Good evening. This is the 43rd lecture of AS and A-level chemistry lecture series. Well, we have been taking this series, and there we have finished the AS level syllabus of totally, and then we started A-level one, and there we have talked about syllabus on inorganic chemistry as well as physical chemistry. And then a part of organic chemistry is in the syllabus, which we now start taking. And the 43rd lecture is on benzene and its derivatives. That means we have been talking about organic chemistry, and that was aliphatic organic compounds in AS level. Now we are taking the aromatic compounds and its reaction uses, etc. So benzene ring, the compounds having benzene rings are commercially very important. Why? Because we use this in medicine, we use this in dyes and plastic and many other uses there. So organic compounds having benzene rings are also called arenes. How it is arenes? Because these are aryl compounds or aromatic compounds. The name arene comes from that AR, aryl compounds are AR, and then we know that we have unsaturated hydrocarbons, for example, alkenes. So ene from here, and AR from here, and then we call the name, general name as arene. So we will have unsaturated hydrocarbon as well as aromatic compounds that called together arenes. When we start first with benzene, isolating benzene, it's 1825 by fractional distillation of whale oil. And then later on, it's fractional distillation of coal tar. And nowadays, we obtain arene from catalytic reforming of fractions from crude oil. The person who gave the structure of this compound, benzene compound, is German chemist Friedrich Kekulé, who suggested that there are 3 carbon-carbon double bonds in benzene and 3 carbon-carbon single bonds. And if we think it about like this, and then this compound should be a distorted hexagonal shaped compound. But with modern analytical techniques, we do see that it is not a distorted hexagonal shape of carbon. It is a planar, perfectly symmetrical molecule. Why this? Then we have to think about this bonding in carbon. You see, this is a saturated carbon-carbon double bond. This is unsaturated carbon-carbon double bond. And this saturated carbon-carbon double bond has got a distance, bond length, I would say 150.154 nanometer. And then a carbon-carbon double bond, it is 0.134 nanometer. And with the modern analytical technique, we see that in benzene, carbon-carbon bond is 0.139 nanometer. So you see that it is in between this saturated and unsaturated bonding between carbons. So then what we could suggest then by X-ray diffraction, we suggested that benzene molecules are not at the corner of regular hexagon, and all bond length are same, not shorter like or longer like single bond and double bonds. So how we do it? We look to the carbon atoms and see their bonding. So here we will see that there are overlapping of p orbitals above and under the plane of carbon skeleton. And that's what we see by experimental electron density map. We can see how it looks like. Now we go for the stability of benzene, how stable it is. So how do we get it? We discuss the thermodynamical data and study of enthalpy, that is energy content, and then we can find out the stability. What is benzene is more stable or not? But that's what we can discuss from the thermodynamical data. So conclusion based on enthalpy changes of hydrogenation benzene. So what we do? If we take a cyclohexene, this is a cyclohexene, you see, this is a cyclohexene, this is a double bond, but these are others are single bond. If we take a cyclohexene and we hydrogenate this, and we get cyclohexane. So cyclohexane, and this reaction, we have an enthalpy changes equal to minus 120 kilojoules per mole that we have measured. Now then, we see, let's say we take the IR data of benzene, and we can see, unlike alkanes or alkenes, benzene ring has got strong absorption in 3050 centimeter inverse and 750 centimeters. All this information, analytical information, says that benzene does not have a normal carbon-carbon bond or even not carbon-carbon double bonds in its structure. So there we see the enthalpy changes of here it is benzene, Kekulé structure is benzene. If we start hydrogenating this, we see an estimated enthalpy is changes 360 kilojoules per mole. But then if we take this structure of benzene, where we show the delocalized pi electrons, and hydrogenate it, and then we get cyclohexane as then measured enthalpy changes minus 208 kilojoules per mole. So there is a difference of about 152 kilojoules per mole, more stable if we take this structure than that of this one. Okay, then we go for the next slide, and here then we know about the stability of benzene. We know how it was named. We know how when it was first discovered, etc. But now we are about to take there. We will see that very many benzene derivatives are very, very important commercially. So when derivatives, how we name them, that is the question. Those compounds, how we name it. So we have a phenyl group. Let's say this benzene, we have just knocked out a hydrogen from here, and then this group now, C6H5 minus. Then this is a phenyl group, and the names and structure started of the derivatives of benzene started from there. And then here are some examples of benzene derivatives, some examples. I do repeat, some examples. So this is chlorobenzene. The molecular formula is 6, that we replaced one hydrogen from here and substituted chlorine, and that got chlorobenzene. Similarly, we can have nitrobenzene, so nitrous substitution. And then we have methylbenzene. This methyl group here is a methylbenzene. Then we have hydroxy group, and this is phenyl group, we said. So this is phenol, and then phenylamine. These are how we start naming the derivatives of benzene. So what we do, the phenyl group is used to name many compounds in where one hydrogen atoms being replaced by another atom or groups, and so on. And then another thing we have to do, this is the structures of some benzene derivatives. 1,2-dichlorobenzene, then 1,chloro-3-methylbenzene. This is methyl position. Why we say 1,2-dichlorobenzene? We number it from here, and then 1, 2, 3, 4, 5, 6 carbon. And because we replaced hydrogen from this one carbon, so we call it 1, and then this 1, and then this is 2. So therefore it is 1,2 dichlorobenzene. Here 1 chlorine, and in the first position, and then 3 in 3 there is a methyl group, so we call it 1 chloro 3 methyl benzene. Similarly here 1 chloro 3 bromobenzene. We can that one, this is a amine group, so I call 3 nitrophenyl amine. Here it's a hydroxyl group, we got 2,4-dichlorophenol. So now we know how we name this, or international naming of this organic derivatives, organic benzene derivatives. So the position here, this position we call ortho, this position we call meta, this position we call para. So it is also abbreviated O, M, and P. So 1, 2, or 1, 3, and 1, 4 substituted benzenes could be 1, 2 is ortho, 1, 3 is meta, 1, 4 substitution is para. So the first compounds in the is called ortho, this one, orthodichlorobenzene, or we call it like this, abbreviated, or dichlorobenzene. Okay, so we have to take care when we replaced the hydrogen atom with any other group. So we have to take care how many hydrogen atoms we have replaced. So here it said we have replaced 1 hydrogen atom by chlorine, so we call it chlorobenzene, is it not? And then we have replaced 2 hydrogen atoms here, and therefore it is the molecular formula is C6H4 2-Cl. So this is dichlorobenzene. This one we call trichlorobenzene. That's what we continue like this. Okay. Next slide. We are talking about, so far we have named the benzene derivatives. So far how the benzene structure is seen, and what are the delocalized pi electrons. For example, when we have carbon-carbon double bonds like alkenes, we see that pi electrons are localized there. But in this case, the pi electrons are all over this, the localized pi electrons. This is the difference between benzene and alkenes, you see. And so another thing is that arenes are nonpolar compounds. We know very well what is nonpolar. And then it has a weak bonding force, intermolecular, and this we named when we are discussing bonding, that London forces between their molecules. The boiling temperature of arenes depends on what? The size and size of the molecules. So the bigger the molecules, the higher the boiling temperature. So, for example, benzene, methyl benzene are liquid, boiling temperature is low, and then naphthalene is bigger molecule than this, so it is solid. So another thing we have to remember, very much remember, that benzene is a toxic compound, and it's also carcinogen. So nowadays, in laboratories throughout the world, benzene has been banned. So we cannot use in the laboratory benzene. This is toxic, seriously toxic. And therefore, what we do if we want to study benzene and it, we take its derivatives and then study it. For example, such a derivative like methyl benzene or nitrobenzene or methoxybenzene, this we take and then study in the laboratory to get more information about benzene and its compounds. Okay. Then we have straight chain alkanes or alkenes. What is the difference? Straight chain alkane or alkenes do not burn in air. Arene burn in air, and a very smoky flame because of the high ratio of carbon to hydrogen in their molecules. another thing we have to remember, that this is not possible because benzene does not combine with bromine in an addition reaction. This is an addition reaction. So this is not possible. It doesn't, because of, if we do so, then we'll see that delocalized pi electrons would be broken. So benzene undergoes substitution reaction rather than addition reaction. And why substitution reaction? Because it wants to keep its delocalized electron retain its delocalized electrons. So for example, here, so we have delocalized electron. Here we have delocalized electron already. So now we go for other properties. Some reaction of benzene, electrophilic substitution reaction of benzene. What we do now here, we not only see the reaction, also see the reaction mechanism, how it works. So addition of bromine without any catalyst. Remember, we can have addition of bromine without any catalyst to an alkene takes place. Then with a catalyst, the alkene will add bromine. The pi electrons induce the dipole in bromine molecules. Here is dipole, pi electrons, dipole. And this is dipole. Okay, and thereby we get this bromine, which attracts the electron here, and then it becomes a cation of bromine. This is intermediate steps. It's intermediate steps. And then we take this one, and then from here, we just substitute hydrogen with bromine. At the same time, what happens? The hydrogen ion is released and from the intermediate cation, and then the hydrogen bromide comes out here from bromine, and this is what is released as hydrogen bromide. This part of bromine released as hydrogen bromide. So we have a mechanism where we see that we have either iron or iron bromide, ferrous chloride, aluminum chloride. These are used as a catalyst for electrophilic substitution by bromine, chlorine or bromine, which occur. And the mechanism is shown here, how we do it. So bromine cation is strongly attracted to the delocalized electron of benzene. Okay, and as it approaches to benzene, bromine forms a covalent bond to one of the carbon atoms using 2 electrons from the pi silicon. This step is an intermediate cation. That's what I said here a few minutes ago. And that breaks down to bromobenzene as 2 electrons are returned to carbon-hydrogen bond to the pi systems of the stable. Delocalized ring is restored. Okay. Now we have seen this bromination of benzene, substitute, how electrophilic substitution. We can also take nitration of benzene or other arenes, and this is also an electrophilic substitution. So what will happen when we warm benzene to about 555 degrees Celsius? Not only benzene, but also we have to have concentrated nitric acid in presence of sulfuric acid. Then the major product is a yellow oily nitrobenzene. Here we have a nitrobenzene. We can name it now. How it is? 1-methyl, 2,4,6 nitro group. So 1-methyl-2,4,6 nitrobenzene. It is also known as TNT, trianitrotoluenes. TNT. It's a very highly explosive compound. We have to remember. So how we prepare it? We take benzene, and then we take nitric acid in presence of concentrated sulfuric acid around 55 degrees Celsius, and then we can have this nitrobenzene. Okay, so what happens? How we get this nitro group? It looks at sulfuric acid is stronger acid than nitric acid, so nitric acid gets protonated in presence of sulfuric acid. So this is what is protonation of nitric acid. Okay, and then this protonated acid breaks down to nitric cation, and water. The overall reaction is nitric acid, sulfuric acid, and nitrogen dioxide cation, and hydrogen bisulfate, and then water. And this one attracts the benzene ring quickly, this one, and then forms this carbocation, and then we get nitrate, and then hydrogen comes back, and then the delacquerization becomes distorted again. So we do get nitrobenzene in presence of nitric acid and sulfuric acid around 555 degrees Celsius. Next one, we will talk about Friedel-Crafts reactions. What is Friedel-Crafts reaction? We want to have electrophilic substitutions of alkyl group or an acyl group. Why we name this? Because this reaction was first reported jointly by French chemist Charles Friedel and American chemist James Kraft, and that's why we name this reaction as Friedel-Crafts reactions. Okay, so do remember that we have to have an alkyl group substitution, electrophilic substitution, and an acyl group electrophilic substitution. And in Friedel-Crafts reaction, halogenoalkane or acyl chloride. This is halogenoalkane, methyl chloride, halogenoalkane. This is as acyl chloride. And we now see that how halogenalkane react with benzene in presence of aluminum chloride catalyst and heat, and we get this methyl benzene, hydrochloric acid. So this cation, methyl cation, attacks the benzene ring, and then we get an intermediate carbocation, and then it gives us methylation of benzene to get methyl benzene. This is the reaction mechanism of Friedel-Crafts reaction for alkyl group substitution. So now we go for, similarly, we can have acyl chloride, and benzene is refluxed with acyl chloride, plus aluminium chloride as catalyst. And this methyl, the final product is methyl phenyl ketone or phenyl ethanol. This is also known as methyl phenyl ketone. So this is another part of Friedel-Crafts reaction. This is a very important reaction in aromatic organic compounds. Very, very important reaction. So here we show how this acylation, mechanism of acylation, this with aluminum chloride, we get this acylium ion cation, and this aluminum tetrachloroanion. And then this acylium ion cation, it attacks the pi electrons here, and then we get carbocation, and then finally we get that as acylation of benzene, we call it methyl phenyl ketone in this reaction. And that reaction mechanism is shown here, how it attacks and these sort of things. We go for next slide, and we talk about addition reaction of benzene with hydrogen. And then the characteristic reactions of benzene involve substitution, because this type of reaction retains the, we said several times, delocalized pi electron with its associated stability. Our addition reactions also involved, but then we can see that this addition reaction, we have to drastic condition. We have to maintain drastic condition. Renin-nickel is a catalyst at 200 degrees Celsius. If we this hydrogenation do, and then we get cyclohexane. But do remember, we do not get hydrogenation unless we use a drastic condition and catalyst. So here again, the hydrogenation, what we are doing, heating and using nickel and platinum to get this, that means cyclohexane. So here, and again benzene, which is, we could get hydrogenation, and then with this condition, we get cyclohexane. Okay, this methyl benzene, if we heat with hydrogen and this, we use this nickel or platinum catalyst, we get this cyclomethane benzene. Cyclomethane benzene. Okay. Chlorination also. We need to use ultraviolet light, and it's a free radical reaction type, and then we can chlorinate all the replace all 6 hydrogen and get chlorinated hexane. Okay. So with this, we will finish our 43rd lecture, and rest of the benzene reactions and other compounds like amine and phenyl and other polymerized organic compounds that we take in our next lecture. Thank you very much for your patience. We finish now today, and we hope to meet again within 2 weeks again.